Welcome to Cerberus. In this video, we're going to be talking about spanning tree protocol. Okay, spanning tree protocol, also known as STP, is a big topic on the CCNA exam. STP can be extremely daunting at first. The good news is STP follows a very strict set of rules. Once you know these rules, STP becomes a very straightforward topic. Before we go any further, it's worth mentioning that there are a few different types of STP that have been developed over the years. The main ones are standard STP, or 802.1d. This is the original STP. PVST, which is the Cisco improvement of STP, adding the per VLAN feature. RSTP, or 802.1w. This is the new and improved STP with a much faster convergence. And Rapid PVST. Again, it's the Cisco improvement of RSTP, adding the per VLAN feature. So you might be wondering, why per VLAN STP? Well, if you have a very large network with lots of switches and VLANs, you can use this feature to help you plan for a more efficient network. You'll see what I mean shortly. Although there are a few different types of STP, they all use a very similar method. In this video, we'll be looking at the standard STP. So what actually is STP? STP is a feature used to prevent loops when using redundant switches. For example, we have 3 switches. They are all linked together, and without STP, a loop could form, causing a number of problems. Now we'll take a look at some loops and the problems they cause. First, remember how switches react to broadcast messages, or a unicast message with an unknown address. The switch will forward that frame out of every port except the one that received it. So if switch B sends a broadcast message, both switch A and switch C will forward that message out of all other ports. Then look what happens. Switch A and switch C receive broadcast messages, so again they forward it out of all of their ports. See what's happening here? A loop has been formed. Now look what happens when switch C sends a broadcast message. Then switch A sends another broadcast message. Broadcast messages are sent all the time, so more and more frames are added to the loop. You can imagine how clogged up the network can get in just a short space of time. The result you see here is called a broadcast storm. Now this broadcast storm will keep getting bigger and bigger and bigger until either one of the switches fail or someone breaks the link by disconnecting or reloading the switch. Okay, let's look at another. Switch B sends a broadcast message. Switch A receives this message. And it does what switches do best. It learns the MAC address of that message. Then look what happens when switch A gets the same broadcast message on another port. Wait a minute, I just got this MAC address on 01. Now you're telling me it's actually on 02? Okay, fine. I'll update my MAC address table. So the switch updates his MAC address table. But then, in the storm we looked at before, the same message will keep appearing in different ports. So all switches will continuously be updating their MAC address tables. This is the second problem with switching loops. Unstable MAC address tables. Let's look at the third problem. For this one, we'll add 2 host computers. So host B sends some data to host A. And again, if switch B doesn't know the location of host A's MAC address, it will flood the frame out all other ports. Now for the sake of argument, let's say switch C does know the location of host A, and it sends the data directly to it. Remember, switch A also received this data, so it forwards it as well. Now switch C, not realizing it's a duplicate frame, forwards the data to host A. Again, see the problem here? Duplicate frames are being sent all over the place. So, what's the solution to all these problems? Well, it's actually pretty simple. The switches simply block one of the ports. The switch with the blocked port still receives the data. It doesn't physically rip its own cable out. It just ignores it. This solves all the problems mentioned. Data cannot loop and therefore no broadcast storms, no unstable MAC address tables, and no duplicate frames. Simple, right? Well, yes, but it's how the switches choose which port to block, which is where it can get a little bit tricky. STP follows a strict process to decide which port to block. Now, once you know this process in detail, STP becomes very easy. We'll start with a high-level overview. Step 1. Elect a root bridge. This is the king or queen of switches. Step 2. Place all root bridge interfaces into a forwarding state. Step 3. Each non-root switch chooses a root port. This is the best route to the bridge. Step 4. Remaining links will decide whether or not to become designated ports. Step 5. All other ports are placed into a blocking state. And that's really it. That's the high-level overview of how STP works. Now, I did mention earlier PVST, which adds the per VLAN feature. This is actually the Cisco default, by the way. So with PVST, you could have this set up for VLAN 1, and by changing the configuration, you can have this set up for VLAN 20. Before we go into the details of how this works, you need to know about the port roles and states. First, let's look at roles. Roles define the job of the ports. Root ports. They are the best port to reach the root bridge. Designated ports. These are ports with the best cost to the root bridge on any other link. Non-designated ports are all other ports that are in a blocking state. We also have states as well as roles. These specify the states the ports are in. Ports can change states while moving from one role to another. For example, root ports and designated ports will be in the forwarding state. We'll take a closer look at states later, but for now, let's go over them very briefly. Disabled, a port that is shut down. Blocking, a port that is blocking traffic. Listening, not forwarding traffic and not learning MAC addresses. Learning, not forwarding traffic but is learning MAC addresses. Forwarding, sending and receiving traffic like normal. It's worth mentioning that listening and learning are transitional states. Ports will enter these states while changing from one role to another. Okay, let's get started with the process. Root bridge election. The way switches elect a root bridge is pretty straightforward. Each switch has what's called a BPDU. The BPDU contains the root cost, which is the cost of the root bridge, the root, and the local bid. A bid, or bridge ID, is a key factor to choosing a root bridge. The first part contains the STP priority, which has a default value of 32,768 plus the VLAN number. And the second part is the MAC address. Simply, the switch with the lowest overall bid will become the root bridge. Now you may not know this, but switches are arrogant. They all think that they should be the root bridge. So they list themselves in the BPDU as the root. They then share BPDUs with each other. Switch B and switch C both quickly realize that switch A has a much better bid than they do. So very quickly they start supporting switch A and change their BPDU to list switch A as the root bridge. Once all switches agree, switch A has now been elected as the root bridge. The next step is simple. All ports on the root bridge enter a forwarding state. Step 3 is for each non-root switch to choose the best path to the root bridge. These are called root ports. The root port decision is based on the port cost. So first, we need to take a quick look at port costs. Okay, here are the costs. As you can see here, we have an old set, which is really the standard set. But the problem is, it was built such a long time ago, they don't really cater for faster ports. This is why we have the new costs. You really want to remember these costs if you're going to take the CCNA exam. You need to be ready to predict the root ports. Okay, so back to the diagram. The important thing to remember here is the root cost is the collection of each outgoing port to the root. Let me say that again. Each outgoing port added together to the root. So let's start with the root bridge. The root bridge will send a cost of 0. It is the root bridge, so there is no cost to reach itself. Then if we look at switch B, it learns the cost from switch A is 0, then it adds its own outgoing cost, which in this case is 4. It then does some quick math. 4 plus 0 equals 4, meaning the root cost out of this port is 4. Switch C also comes to this conclusion. Now they both know they have a root cost of 4. They then send this to each other. Again, they do some quick math. 4 plus 4 equals 8. This means they now have one port with the cost of 4 and another with the cost of 8. The root port is based on the lowest cost. So in this case, they both choose the port with the cost of 4. So in this case, everything has worked out fine. But there may be times where the root cost is the same on multiple ports, such as duplicate links or when the cost has been changed manually. Then what? In this case, the decision comes down to some tiebreakers. These are the lowest neighbor bid. We looked at bids earlier when electing a root bridge. Then if they tie, the lowest neighbor port priority. Now ports can have their own priority set. And if they tie, it's the lowest neighbor port number. This is the actual number of the port itself. Okay, now designated ports. In this step, the designated ports are decided. Links that are not root ports will go through this to decide whether or not to become designated ports. And it is decided like this. First, they look at the lowest root cost to the bridge. If that ties, they look at the lowest bid. If that ties, again it goes to the lowest neighbor port priority. And if that ties, the lowest neighbor port number. So it's pretty similar to the tiebreakers of root ports. In this case, switch B becomes the designated port. Blocking. The last step in this process is a very simple one. Every port that is not either a root port or a designated port is put in the blocking state. And this is the last step of the STP election process. Now look, I know it's a lot to take in, but trust me, once you go through these steps, practice it, and you learn it, you will have no problem answering any questions on STP. STP very rarely goes wrong. Usually it's just a case of working out what decisions STP has made. Okay, so the last thing I want to talk about is the kind of downfall of STP. Convergence. That is the time it takes to do all the work and become stable. Standard 802.d STP was designed quite some time ago. At this time, if it took a minute to converge after a change, it wasn't a big deal. Nowadays, where almost everything we do relies on network access in some way or another, especially the likes of IP phones and video calls, even a few seconds downtime can cause problems. Before we look at the convergence process, we should first look at the timers and what they mean for the port states. Hellos. The hello timer, by default, is every 2 seconds. This is the time interval where the root bridge will create and send hello messages. This lets everyone know everything is still alive and kicking. Max age. Max age is 10 times the hello timer by default, so that's 20 seconds. This is the time the switch will wait before it realizes something's wrong. Forward delay. 15 seconds by default. This is the time between the listening and learning states. We will look at this now. So we looked at states earlier. Let's take another look. The forwarding state. This state can move directly to blocking. A blocking state can't move directly to forwarding. It must first enter the listening state. The listening state, this is where the port listens for MAC addresses, but without learning any. This is in order to stop any potential loops. This is held in this state for the forward delay, which is by default 15 seconds. After 15 seconds, it enters the learning state. This is where the switch starts to learn MAC addresses. Again, it's held in this state for the forward delay, which is 15 seconds. After this, the port can then move to a forwarding state. So do you see the problem here? Let's take a closer look. Let's say the link between switch A and switch B goes down. Switch B will stop getting hello messages from switch A. First, it will wait for the max age timer, which is 10 seconds. Then, realizing something's wrong, it will have to react by moving its link to switch C to its root port. But this is the problem. A blocked port cannot move to a forwarding state right away. It first needs to go through the other states. First, listening for 15 seconds. Next, it's learning for 15 seconds. Only then can it enter the forwarding state. Now everything's working again. Great. But from the link going down, it took 50 seconds to reconverge, and in today's network, that is a hell of a long time. And this isn't just for ports connected to switches. If you've ever plugged a computer into a real Cisco switch, or even used Packet Tracer, you may have noticed that it takes a few seconds for it to turn green and start working. This is because STP is running through the listening and learning states. There are a few things we can do to help speed up the general convergence, such as port fast and BPDU guard, but that really is for the access port, so the ports that connect to devices like computers. The best thing to do is to actually use the new and improved Rapid Spanning Tree protocol. As I'm sure you can tell by the name, it's pretty fast. Much faster than standard STP. We'll cover our STP in another video, but don't worry, the core concepts stay the same. There are only a few very basic differences. For now, rewatch this video, learn the process, and practice it over and over again. Once you get this process down, STP really does become a simple topic. That's it for STP. If you like this video and you want more, you need to let us know. leave us a comment, like, and subscribe. As long as we keep getting the great feedback you guys have been leaving us, the videos will keep on coming. Thank you for watching.